Okay, so it's a quick video to go through the multiple choice. Number one, okay, which letter represents the most probable energy of molecules at a higher temperature? The higher temperature is this line, because it's got more area to the right hand side. The most probable energy is the peak, which and the energy, remember this here, B represents particles, remember the axis, number of particles, but this here represents energy. So number one is D. Okay, here we got a graph showing the volume of gas with time, excess magnesium with sulfuric acid. So limiting reagent is the sulfuric acid. Which line represents the volume of hydrogen formed at the same temperature and pressure and the concentration is halved? So you halve the concentration, you'll have half the gas because it's already a limiting reagent. So we want it to go up about halfway. And also, if you half the concentration, you're going to pretty much half the rate, or certainly have a slower rate. So we're looking at a less steep graph. Okay, and I'd say out of all those, that is A. It's not D because that's still as steep, if not steeper. Okay. Another Boltzmann question. What does the area under the curve represent? So the area under the curve represents the total number of particles. Okay, so that's B. It's got a number of particles who react to each other. That would be the ones that are past a certain activation energy. There's no activation energy here. The total area under the graph represents the total number of particles. Okay. Question 4. So, what is likely to decrease the accuracy of the experiment? So if you imagine they're trying to see a cross through here, a precipitate's formed, precipitate of sulfur normally in this reaction, I think this one is. As a precipitate's formed, it makes it harder and harder to see until eventually stop the clock. Okay, now the hydrochloric acid is one of the reactants. If you're rinsing your flask out of that, you're going to end up with some additional hydrochloric acid in there. So that's going to decrease your accuracy. Okay, so I would say for A. If you stir it consistently for each one, that shouldn't make any difference. Using the same piece of paper is exactly what you should do. And using different measuring cylinders shouldn't make any difference if you're using them all correctly. But the significant difference would be A. Let's just talk about the same experiment. If it was repeated at 20, the experiment was repeated at 20 degrees using 250. So how's that different to before? Was that before they were using 100 centimeter cubes? Okay, so imagine we've gone from one like that where it'd be quite full to one that's like this, and it's more spread out. That's going to affect how quickly you see the cross. There's more precipitate on top of itself here that blurs out the cross more quickly. Okay, so the time taken would actually be increased because the precipitate is spread out, so you need a lot more of it to blur out the cross underneath that you're trying to view. Question 6. Series of experiments were carried out to find the order of reaction with respect to reactant X. In these experiments, only the concentration of X was changed. Which graph would show the reaction to be second order? So it's rate. So all of these then should be if it's first or second order, they should be pointing up, not down. The rate should increase with concentration. So that means it's C or D. C is first order, D is kind of like a y equals x squared graph, that is second order. So the answer for question 6 would be D. Okay, so on this one, what we can see is basically saying everything stays the same apart from the H plus, and it's caused the rate to be divided by 4. We can see that the H plus concentration is first order, so it's directly proportional to the rate. So if the rate's been divided by 4, the H plus concentration must be divided by 4. So the H plus concentration to begin with, we can work out from here, 10 to the minus pH, so it's minus 0.7. Okay, we can divide that by 4, because the rate was divided by 4, which gives us 0.04, 4988 moles per dm cubed. But we need that in a pH, so we minus log it, and that gives us 1.30. So it's B. Okay, so when the concentrations of W, X and Y are all doubled, so Y is catalyst, W and X are reactants, the rate of reaction increases by a factor of 4. Okay, so which is possible? It's very possible. Some of these aren't possible. So if this was doubled and then squared and then that's times by 2, that would equal times by 8. So it's not that one. This one, same thing, isn't it? Doubled times by 2 would equal 8 as well. X and Y both doubled, would times them together, make times by 4. So question 8, the answer is C. Just go on to this one. Z's a product, so that's irrelevant. And X, I'll just times it by 2. So it's C. Right, so there's a lot of information in question 9. Told us that we've got a propanone, it's reacting with this diol here, and we've added this. Now this benzene sulfonic acid is not in the overall equation. Okay. When the concentration of it is doubled though, the rate doubles. So does that mean it's first order overall? We don't know anything about what, we can't say that because we don't know what effect this one and this one has. Overall it's about all the reactants and catalysts. Is it third order overall? We don't know again because we don't know about how propanone and the diol affect it. The reaction is acid catalyzed. Well, it must be because when its concentration of the acid is doubled, the rate's doubled. And it's catalyzed because the acid is not in the reactants. So question 9, the answer is C. We don't have enough information to work out the units. Right, Josh. Right, okay. Correct units for this rate equation. So rate constant, sorry, K equals moles per dm cubed per second over moles per dm cubed like so. So that will cross out there, that will cross out there, that. So we get moles to the minus 2, dm to the 6, s to the minus 1, which is D. So 10 is D.
I've got the first one.
Okay.
There are 3 groups of 4.
Okay, so you've got H plus concentration here. You've got to work out the H plus because pH doesn't directly go in there. So you're going to have to do 10 to the power of each minus pH here. So we got 1. Naught point 0.01, 0.001, 0.0001. Okay, and then you've got to square each of these and then times it by, ignore that column for now, times it by each one of these, and you've got to find which one will give the rate be the slowest. Okay, so out of all those, it is C. Okay, so thing to realise here, they're all gases. So at fixed temperature, the reaction is compressed to triple the original pressure. That means that all concentrations are going to be times by 3. So we've got times by 3 times by 3. So overall, the rate is going to be times by 9. So the answer is B. Okay. Okay, so on this one, it's important to realise that this line here, so that means we can pretty much just scribble out that line there. It's a bit of a tricky one because x is never the same twice, but it's easy to work out x. You can see that's been times by 2, that's constant, that's been times by 4, so the order of x is 2. So 4 there. Okay, now if we're looking at, I'm going to do this one here, so that has actually been timesed, well, it's been times by 0.25, hasn't it? Okay, from here to here, that's been divided by 8, so in other words, times by 0.125. Okay, and this has been times by 2. So we know x is 2, so it's 1.25 squared. We know y is 0, so we can ignore that. So z, z has been times by 2, so 2 to the power of x, and this is like so. So we're rearranging to find x. So like this. Okay, basically 2x equals 2, so x equals 1. Therefore, the order of z is the order of 1. So the overall order, get there in the end, is 3. So that gives you D. Okay. Right, the reaction below is first order with respect to A, where the initial concentration is 1 moles per m cubed, the half-life is 20 minutes. What is the half-life and the initial concentration is 2 moles. The half-life is constant. Okay, so for 14, the answer should be the same as what it was before, so it is B. Right, we want a rate equation. Okay, so we're looking for the slow step is the rate determining step. So we can see that we need NO2 and NO2 reacting together. So we've got 2 NO2s in the rate determining step, so it must be C. 50 is C. Okay, which is a concentration time graph. Okay, so it's 0 order, but that doesn't mean it's not C, because if it's a reactant, it is being used up. Okay, it's just the rate is constant. So in a concentration time graph, that means that the gradient is constant. So 16 is A. (17). These are rate concentration graphs now. It's first order with respect to x. Okay, so the rate increases linearly with the concentration, so that will be A. Okay, 18. Which statements explain why reaction rates increase as the temperature increases? Activation energy is less. No, activation energy doesn't change. Collisions between the molecules are more frequent. That's true, because the particles are moving faster. A great proportion of molecules have energy greater than the activation energy. That's true. So it's 2 and 3, which means 18 is C. Okay, 19. That's very clear. That's 1 over T. That says there. So graph NNK over 1 over T. Okay, for the reaction as a gradient. Sorry. Gradient of this. So we want to work out the activation energy in kilojoules per mole. So that we know, as always with these graphs, equals minus EA over R. So EA equals minus 4420 times by minus R. Okay, that'll give you answer in joules per mole. So you have to divide it by 1,000. Get into kilojoules per mole. And if you do that, you get C. Remember, R is a constant, 8.313. Right. Last one. What is the main reason for the increase in reaction rate with increasing temperature? Activation energy does not change with temperature. Okay. The main reason is not so much about how often they collide, it's more to do with how much energy they have. Think about the Boltzmann distribution. Yeah. You're increasing the proportion of molecules past this point. Okay.